So, welcome everyone to the last day of Qiskit Fall Fest, and it's our pleasure to have Timur Matil from IBM Quantum, France, to deliver the first lecture. Simon is a quantum software engineer working at IBM Quantum France. He specializes in quantum circuit compilation and optimization. He develops methods to adapt and optimize quantum circuits to real-world constraints. He has been actively involved in European quantum initiatives and contributes to both research and industrial collaboration with the quantum ecosystem. Today, he's going to talk to us on low overhead error detection with space-time codes. And it's my pleasure to welcome him to deliver our first lecture of the day. Welcome.
Thank you. So can you hear me well and see my slides? Everything is okay? So yes, this talk is about some way of mitigating errors that we call error detection, which is some like loose form of error correction where we don't correct, we just post-select away errors. And this is a joint work with Ali Javadi, who is also a researcher at IBM, but based in New York. And I will try to run you through the construction of those error detection codes, like low overhead error detection codes, and how we can use them to actually do useful quantum computation. So this talk is about basically error mitigation, but not in a traditional sense of error mitigation. So usually when we talk about QEM, we usually think of things of the style of PEC, where you have some kind of circuit with some noise channels. So here, those are the lambda i's in this picture here. And we kind of virtually invert those noise channels by adding the inverse noise channels, which are non-physical noise channels, but that we can emulate by running many times the same computation. So basically, we pay a price of sampling overhead in order to counteract the action of errors. And at the end, the cool thing is that we can get unbiased estimates of some observable, for instance. So this is, for instance, the PEC framework. And on the right-hand side here, you have the other end of the spectrum, which is quantum error correction, where you take one logical qubit that's encoded in many physical qubits. So for instance, this is a picture of the bivariate bicycle code that we intend to use at IBM Quantum, that stores 12 logical qubits within 144 physical qubits. And then you need to have all of them entangled and interacting strongly in order to implement some quantum error correction scheme that will detect and correct for errors. And the cool thing here is that you pay a huge overhead in terms of number of qubits and gates, but you get basically very strong error suppression that brings you to a regime where you can run very large quantum circuits. So this is really, those two techniques are both ends of the same spectrum, where on one side you have a few gates, you can run a few gates and pay a price of exponential number of samples. And you can only basically do expectation values because those techniques rely on statistical analysis of many runs. And on the other hand, you have quantum error correction, where you can run millions of gates with many qubits, and you get fault tolerance, meaning that you can have single-shot access to a good quality quantum state at the end of the computation. And the result I will present today is based on error detection, which is somewhat in the middle between both ends, where we can use extra qubits. So we do modify the circuit by adding gates and qubits. And we still get also some exponential scaling in samples, but we have single-shot access to good quality quantum states instead of having only expectation value access. So, for instance, if you consider some n-qubit quantum circuit with m gates that's running on a quantum computer, and each gate comes with some gate error p, then we can roughly estimate the fidelity of the resulting state as 1 minus p to the m. And we can ask ourselves, what will be the overhead in terms of resources in order to bring this fidelity that can be quite low, exponentially low in m, to some better fidelity f prime, which is, let's say, 1 minus epsilon for some tiny epsilon. So in the regime of quantum error mitigation, what the theory tells us is that you can do everything without adding any qubit. You can just run many times the same circuit. And the sampling overhead will scale roughly as this quantity here. So basically, at the bottom of this fraction, you can recognize the fidelity and the original fidelity. And at the top of the fraction, you can see that's the target fidelity. So basically, it's a ratio of the fidelities to the power 4. And usually, f is exponentially small, exponentially smaller than f prime. So you have something that grows as some exponential to the power 4. So it grows very quickly. And in this framework, you don't have access to single shot. You can't, for instance, have access to good quality bit strings out of the mitigated circuit. You only have access to expected values of some observable. On the other hand, if you look at QEC, so quantum error correction, you will pay quite mild qubit overhead, but still quite huge in the current scales of hardware. So you will pay a price that's basically linear in the number of qubits and polylogarithmic in the error you want to achieve. You will pay this price in terms of qubit and gate overhead, basically. And no sampling overhead, because every time you run the circuit, you should correct errors, so you get good quality results, and you have single shot access. And in the middle, we have quantum error detection, where we use a very mild qubit overhead, so let's say constant number of additional qubits. But the theory tells us that the sampling overhead should grow as just the ratio of the two fidelities, meaning that we get basically a quartic runtime improvement compared to traditional QEM techniques. And this is what we will discuss today. So how can we detect errors within a quantum circuit? So the first standard method is to add symmetries to the circuit we are running and verify that the symmetries are satisfied at the end of the run. So, for instance, if you are trying to embed some kind of fermionic dynamic inside your circuit, and you know that the dynamic is particle number preserving, for instance, you can check that the particle number is what you expect to be at the end of the run by measuring the state, and discard any run that leads to something that falls outside of the range of particle number you are expecting. So this is one very simple way to actually check for errors. So basically, you have to embed some symmetries within your dynamic, within your circuit, and check that those are satisfied. You can use error detecting codes. So those are just codes where basically distance 2 codes that do not allow for you to correct errors, because those codes can't correct any error, but they let you detect weight 1 errors or some broader set of errors. And you can use those to encode your qubits and then just really detect via the same thing you will do in a quantum error correction code, where you measure syndromes, you can detect errors and throw away any runs that contain errors. And yeah, this is usually like the most direct approach, but usually the overhead is quite large. For instance, if you look at the bottom code here, in order to encode 3 qubits, you need 8 physical qubits. And this is just space overhead. This does not take into account the fact that then you need to implement logical gates onto these encoded qubits, and this can lead to a quite large gate overhead. And the approach we take in this talk is another approach called coherent Pauli check. And the idea is that we can start from a Clifford circuit that we want to correct. And we can basically check that this Clifford circuit sends some random Pauli onto some other random, some expected Pauli, and check this type of symmetries and use those symmetries to detect errors. And this is exactly what I will discuss today. So why do we want to correct errors in Clifford circuits, since Clifford circuits are a priori very simple to simulate and not very interesting in terms of quantum computation? So the reason is because like most near-term applications, they rely usually on Clifford-dominated circuits. So for instance, if we have a circuit that has huge chunks of Clifford gates that contain all the entanglement generation, for instance, of the circuit, then we can correct errors, detect errors on those chunks and vastly improve the quality of the overall circuit. Also, like we know that there are university results that state that, for instance, you can start from magic state inputs and apply a huge Clifford and still get universal computation. So if we assume that the magic state inputs can be prepared with high fidelity, then remains to correct the huge Clifford unitaries that we will apply on those. And this can be, like we can improve the quality of this huge Clifford. And there are also many quantum advantage proposals that rely on huge chunks of Clifford gates. So for instance, you can conjugate a Clifford circuit using arbitrary unitaries, and this is a hard sampling task. You can prepare graph states, which is a huge Clifford circuit, and then rotate the qubits in a random basis and measure. This is also hard. And you can also rely on the fact that like highly entangled states are resources for measurement-based quantum computing, and use this fact to derive hardness of some sampling tasks. So how does Korean polycheck work? The idea is the following. So you start with a payload circuit, which is this U in the middle. So you can think of U as the actual thing you want to run, which is a huge Clifford circuit. You can add an extra qubit, start in Ket0, apply Hadamard, and do a control L on the left of U and a control R on the right of U, and then measure your qubit in the diagonal basis. And here L and R are related through U, meaning that basically if you pull L through U, you get another Pauli operator which coincides with R. So those two L and R should cancel each other, meaning that the syndrome we expect to measure on the check qubits should always be 0 in the case where there is no noise. And this is true for any appropriate pair of L and R. So basically, if we measure something that's not 0, it means that some error occurred within U, some errors that anti-commuted with R. And so we can discard the run if this happens. And each control L or control R can be implemented by basically a cascade of CNOT gates, roughly. And we can stack them. We can do many left and right checks by recursively applying this construction, and hopefully catch more and more errors. But the idea is that every time we add a new check, we add basically a linear number of control NOT gates, and this is without even considering the fact that we actually need to implement that on the hardware. Like if you really want to implement this circuit on the hardware, you might need to insert some swap gates, you might need to route information through a layout of qubits that will add even more gates than just the one I'm depicting here on this picture. So it's really critical here to reduce the gate overhead in order to efficiently probe for errors. Because if we add too many gates when we try to detect errors, what we'll end up doing is add more errors than we actually detect, and we'll end up just making things worse than before, and discarding shots where we basically introduced errors instead of just trying to remove them. So we need to be smart in the way we implement those checks. So on the right, so here is just a rough space-time picture of quantum circuits in 3D, just to give you an idea of the construction we are doing here. So in circuit A here is like just a brickwork circuit of CNOT gates. So it's like each blue box here. I don't know if you can see the picture well, but each blue box is a CNOT gate, and we just stack them in a brickwork manner to build a very complicated circuit. And you can think of each blue box like blue boxes being separated by random single qubit gates in order to make things very random. And if we were to apply the state-of-the-art techniques of let's say, write-only checks from the literature, we'll end up with the circuit on the right, the B circuit here. So the blue part is just the thing we actually want to run, and the purple part is all the additional gates we need to add in order to implement exactly this picture on the right, where we removed all the left checks because in some settings we can actually remove them. I don't want to go into the details. So we only implemented the right checks. But since we constrained the qubit on a line, you can see the layout on the left here, we had to insert many swap gates, and the resulting circuit looks like this. So basically, you can just quickly grasp that there are way more purple gates than blue gates, and you can guess that this is not going well. If we try to actually run this circuit, we will end up just measuring pure noise because we completely destroy quantum information by adding too many gates. On the bottom left here, you have a picture of the same circuit, except we used our technique that I will present today to insert checks. So all the purple gates you can see are probing from the side. You can see the layout on the left here. Probing from the side of this blue payload circuit in order to implement the same type of checks, except the checks are embedded within the payload and are thus leading to a way milder overhead and hopefully a better performance. And if we try to simulate, here it's just a simulation, right? We try to simulate both circuits and see how they perform in terms of how many runs we discard and what are the quality of the shots we keep. You can see that, so the light green is the B circuit and the dark green is a C circuit. You can see that using our technique, so the C circuit, we get basically, we discard 1,000 times less shots than what we do with the right circuit. And we still get a 17% better fidelity assessment, like of the final state, compared to the state-of-the-art technique. And this is greatly due to the fact that we use roughly 2 times less gates to implement the same type of detection. So basically, if we can reduce gates, we can improve post-selection rate and fidelity, and this is exactly what we want for this type of applications. So how does it work? So here I will just give you a rough idea of the main process that we do to pick those weird space-time checks, and then I will go into the details of the math and how it works. Okay. So the idea is to start with some Clifford circuit C that's already laid out on the hardware. So it means that it's already, if you want, transpiled, and we can actually already run the circuit on the hardware. And so since we assume that we are not using the full qubit chip, we can actually find some adjacent ancilla, which is this purple qubit here, that's connected to some data qubit. And we can identify all the internal wires of C that are corresponding to this data qubit. So here I have this purple qubit that's connected to the second data qubit. So I can isolate all the internal wires of the corresponding to this second qubit here. So those are the red box. Then what I can do is I can find a low weight check on those wires. So I will define what are low weight checks. So basically it means that I can find a way to add Paulis onto those wires in a way that don't disturb computation. And on top of that, I can also estimate how using this check will improve the error rate of my payload. So maybe some checks are really good, some other checks are really bad. Some checks are, for instance, inserting more errors than they can detect. So we want to discard them, but some other checks are catching a lot of errors, so we want to use those. And this we can do. Then once we have this, the best check we could find, we can actually allocate this extra ancilla and implement the check by doing the control, basically preparing the qubit in the plus state and doing the control Paulis corresponding to each of the Pauli we found at the previous stage, and then measure the qubit in the diagonal basis. And then we can repeat this process in order to add more and more checks until we are satisfied with the error rate or until we run out of extra ancilla. So the way it works is that we first need to understand what are valid checks. What are basically the valid Paulis we can put on some internal wires in a circuit in order to not change the overall Clifford we are implementing. And this is a key notion when we pick Pauli checks. So if we start with some random Clifford circuits that looks like this, we can, for instance, add some Paulis inside the circuit. So here I just added 4 Paulis, so those 2 X at the beginning and this Z in the middle and this X at the end. And we can iteratively propagate backward all the Paulis inside the circuit. So here I just propagated backward the 2 initial X gates that were already at the beginning, so I didn't do anything. Then I can propagate this Z Pauli here at the bottom. And if I run it through all those Clifford gates, I will end up with a Y on the last qubit here. And then I can backpropagate this last X gate, and I end up with a X on the first qubit and the Z on the last qubit. So I don't know if you're familiar enough with Paulis, but if you look at those Paulis, you can see that those 2 X here will compensate themselves because it's like corresponds to a bit flip. So 2 bit flips in a row, it's like doing nothing. So those 2 X's actually implement the identity. And at the bottom here, you have a X, Y, and Z. And if you multiply all of them, you get basically the identity up to a phase. But basically what I want to show here is that when I backpropagated all those Paulis, I get the identity at the beginning. This means that those 2 circuits are equivalent. Like if I go back here to this picture, those 2 circuits are completely equivalent and they implement exactly the same unitary up to some global phase. And this is what we are looking for. We are looking for ways of sprinkling Pauli gates throughout the circuit such that they don't implement different things. They implement exactly the same thing as the original payload. And once we have those Pauli gates and we know that they don't change the overall payload, then we can implement the check by just allocating this extra qubit here at the bottom and implementing the controlled version of the Paulis. So here I have a X gate, so I implement a CX gate, so a C0 gate. Same thing for this bottom here, this bottom gate here, and this Z gate become a CZ gate here. And this X gate become a CX gate here. And then I measure my qubit in the diagonal basis. So how can we formalize this process? So we can define some operators that we call the backpropagator, which I denoted by B here, that takes a Pauli, a single qubit Pauli, and some internal wire of the circuit. And it basically gives me the operator P I would get by backpropagating my original Pauli to the beginning of the circuit. So here I drew by hand, sorry, some picture. So if I have some internal wire in the middle of the circuit, I can consider adding a Pauli P here at this location in the circuit. And I can basically, once I specify this wire here, it kind of splits my circuit in 2 parts, like what comes before the wire and what comes after. And I can backpropagate my Pauli PW back to the origin, like to the beginning of the circuit using this formula here. And this gives me exactly my backpropagator. And what I'm looking for is a set of PYs and WYs, so a set of locations in the circuit where we add a Pauli to each location, such that if I backpropagate everybody at the beginning of the circuit, I get the identity. So like multiplying all the backpropagator gives me the identity. And this, by definition, tells me that adding those Paulis will not change the circuit. And I can even relax this constraint if I have access to some stabilizer at the beginning of the circuit. I can also relax this constraint to actually having the product of the backpropagators belong to some stabilizer group, which lets me find better checks in some cases. And we can also do cool things like characterize exactly what are the logical errors that will be caught by a given checks using something that we call the back cumulant of the check. And we can also, using those back cumulants of checks, efficiently like do some kind of efficient Monte Carlo simulation of the error model to actually assess what will be the final post-selection rate and the final logical error rate, and also the fidelity if we need. So this lets us actually score checks and say that one check might be better than another one. And for this, actually, we can use this very nice result by Nicolas Delfos and Adam Pesnik to actually speed up quite a bit simulation of the Monte Carlo simulation. Instead of forward propagating errors, we can backward propagate checks and use this to reduce the number of times we have to back propagate Pauli gates. So how do we find good checks? So remember, what we are interested in is to actually find a set of Paulis such that when we back propagate everybody, the product gives me the identity. In fact, what we can do is use what we call the symplectic encoding of Pauli operators to turn those back propagated Paulis into bit strings, and then finding a bunch of Paulis that back propagate together to the identity boils down to finding some bit string that lies within the kernel of some matrix B. And this also lets us do cool things like restrict the search to some fixed set of wires within the payload. We don't need necessarily to look for a global check that acts on the full payload. We can actually pinpoint, for instance, one qubit and look at all the wires of that precise qubit and only look for a check that's located on that qubit. And finding a low weight X will give us basically the few Pauli gates we need to add in order to have a valid checks. And this can be done using a standard decoding algorithm. So for instance, if I pick this circuit at the bottom, which is quite a big circuit, and I say that I only want to pick checks that are located where the Paulis will be located at the green positions at the bottom here. Then I can I can basically look for all the positions that I'm interested in, back propagate Pauli X and Pauli Z, and this will specify the full set of valid checks. And I can basically encode all those back propagated Paulis into a huge matrix that you can see on the right here. This is the actual matrix I can get out of my code by back propagating all the green boxes, basically. And then within this huge matrix B, I can look for some X that will lie inside the kernel of this matrix. And one way to understand what we are looking for is basically what we are looking for are rows of this matrix, such that when we XOR those rows bitwise together, we end up with the 0 bit string. So here, if I did things correctly, if you XOR all those red bit strings, you should get something that boils down to a 0 vector, maybe up to the last component, because I'm assuming that I'm starting in state K0, which gives me more freedom to pick checks. So once I found the rows that I need to XOR together to get some 0, so when that satisfies this equation, basically, I can go back to the Pauli world and understand that I need to add, for instance, a Z here, a X here, a Y, and an X here, and then implement my check using an extra ancilla. So yeah, I start with this circuit, and I end up with that circuit by adding the remaining checks. And once I added this extra ancilla and the extra gates, I can actually easily compute what are the errors that are caught by this check, because I know that I will need to measure the Z operator at the end of Q6 here, because this is my check qubit. And I can back propagate my Z operator through the circuit, and all those green boxes here will correspond to locations where the check acts non-trivially and will basically catch errors. So you can see that basically the detecting region grows here slightly and then shrinks back to a single qubit. And all those green boxes, you can think of them, as locations where errors will be caught within the payload, thanks to our check. So the cool thing is that then since we have access to this region, we can do Monte Carlo simulation and say that most errors in this region will be caught, and we can assess how the error rate will improve thanks to this check. So to summarize how it works, we start with a plain circuit. We isolate some wire. So here I picked the middle qubits here. Given the like qubit wire here, we can look at all the possible positions where we could insert Paulis, use the decoding algorithm to find a valid check that consists in the least possible number of Pauli gates. So here we found a solution with three Pauli gates. Then we can implement the corresponding check, which will add those extra purple gates here. And then we can use the back cumulant of the check, which are all those green boxes, in order to assess what will be the new logical error rate after implementing the check, and decide if we want to keep that check or find a better one. And the cool thing is that even a low override check, so here this is a 3D picture of our construction, even a very low override check, so here, for instance, we have a weight 3 checks where we only insert 3 Pauli gates. This can lead to a very large detecting region. So if I backpropagate, once I implemented the check, if I backpropagate the final measurement, I get quite a huge region of this circuit that's covered by the check. And so basically, just by spanning only 3 CNOT gates, I can catch many errors inside this circuit. And also, this approach works for any connectivity. I can map my circuit, for instance, to a grid and have neighboring qubits probe to the side of my payload qubit, my payload circuit, in order to go and detect errors within the payload. So this gives us a very simple error detection strategy where we first compile the Clifford payload to some layout on the machine. So for instance, this is the layout of our quantum processors at IBM, and the blue and green qubits are the data qubits we are using to implement the Clifford payload. And then I can use neighboring ancilla, so all the red qubits here, to go and probe at the green positions this payload from the sides and implement the checks. So here on the right, you have 3D pictures of what it looks like on a 3x3 grid. So the blue only picture corresponds to some kind of random brickwork circuit on a 3x3 grid, and all the purple boxes I'm adding here corresponds to the checks that we probe inside the payload. And yeah, I can also add many checks probing the same qubit, and basically the idea is that I can pick a few checks on the same data qubit and then use swaps in order to exchange the check qubit positions when they need to interact with the data qubit. And actually, we can even be smarter and use half swaps that are cheaper than swaps and that actually help the checks check each other and increase the fidelity of the overall process. And we can also do that on very large scale payloads. So for instance, this is I believe a 30 qubit payload. So all the blue boxes are part of the payload. So this is 30 by 60 circuit, so it's quite deep. And we went and added many checks at position regularly along the payload in order to implement all those red boxes that will go and check inside the circuit. Yeah, so this is just something I already discussed, so I'm skipping those slides. The cool thing about this framework of this decoding-based framework is that we can also deal with circuits that contain non-Clifford gates. So everything I talked about here relies on the fact that we can propagate Paulis through the circuit we are trying to detect. And this assumes that the circuit itself is only Clifford. In some cases, we have, in any interesting cases, we should have non-Clifford gates somewhere in the circuit. And we can actually generalize this framework where basically we can we can use the same B matrix encoding and decoding algorithm, but adding also the constraints that the checks we pick need to kind of not interact with the non-Clifford rotations that are within the payload. And this is something we can formulate. The main issue of that is that if we look at the space of valid checks, that's basically the kernel of this B matrix we saw before. They form a linear space in the kernel of this matrix. And we can look at the dimension of this space. And we can show easily that every time we add a non-trivial rotation, a non-Clifford rotation inside the circuit, we basically reduce the dimension of this space of valid checks by 1, meaning that we effectively divide by 2 the number of valid checks we have access to. So it means that we will shrink exponentially fast the set of valid checks by adding more and more non-Clifford rotations. And consequently, like the huge drawback of this technique is that if we have a very highly non-Clifford payload, we will end up having a very tiny valid check space, meaning that we can't find any good checks, and the logical error rate and post-selection rate will suffer from that. And on the right here, you have simulations where we picked a random Clifford circuit and we added more and more rotations inside this circuit. And every time we add rotations, we try and pick new checks and assess what's happening. I lost my slides, sorry. Okay. So every time we add new checks, we basically degrade the logical error rate and the post selection rate. So you can see that we basically start at the bottom where we can have a very good post selection rate, and then every time we add checks, we go up and up, meaning that we detect less and less errors, and the logical error rate consequently also increases until basically you can see when we add 100 rotations on this payload here, we can't detect any errors and we barely improve the error rate. And nevertheless, what we did is to run experiments using only Clifford circuits where we tried to prepare the largest possible stabilizer state using very large Clifford circuits. And this we ran on our Heron 2 IBM QPUs. So at the bottom here, you have the layouts we used inside the qubit layout of the processor, and you can see that we increase the payload size from basically 14 qubits. So here, payload size is just the blue qubits, which are the data qubits, and the purple qubits are just the check qubits. So we went from 14 up to 50 qubits, and we ran the experiment and ran the shot discarding process and estimated the fidelity of the resulting state we get at the end. And so you can see that the post-selection rate, like as expected, kind of decreases exponentially fast with the number of checks we add, and also with the number of qubits we have in the original payload. But we can see that we can get quite significant fidelity boosts using this technique. And you can also see on the right the number of entangling gates overhead we implied by our technique, and you can see that there is a mild increase of actual CZ count compared to the number of checks, but this is quite a mild gate overhead. It's not like this is mainly the reason why we get such large fidelity boosts, because we don't add too many gates to detect errors. To give you an idea of how we implement how we compute this quantity here, the fidelity, and how the experiment looks like. So we estimate the fidelity by sampling random stabilizer of final state. And we did that using roughly 10 stabilizers and 1 million shots per stabilizer. And to give you an idea, if you look at the blue curve, maybe we can see it better here. So this blue curve, dark blue curve, corresponds to the 32 logical qubits experiment. And so we can see here we have basically a post-selection rate of 10⁻⁴, meaning that we keep one run every 10,000 runs. And this actually this point here takes roughly 43 minutes to run on the QPU. So it's still quite fast. Even though we have a very low post-selection rate and we do a lot of shots, we still get roughly 0.1 logical shot per second, meaning that we get one valid shot that passes all the post-selection every 10 seconds, which is completely reasonable for some applications. Like there are some applications that don't require that many shots, and here you will have one valid shot every 10 seconds. So maybe in 1 minute you can have a dozen of shots and scale well this way. And also, what we had to do to achieve those results is to take care of readout errors, because readout errors are quite high in superconducting qubits. And the way we did that is, since we want to measure a final stabilizer, which is basically a final Pauli at the end of the circuit, what we did is to use CNOT gates to kind of fold this stabilizer onto a few qubits that we had to measure. And we were able to basically pick the best qubits that had the best readout errors and fold the stabilizer using CNOT gates, extra CNOT gates that were not error detected, in order to reduce the overall impact of readout errors. So those are the numbers we get. So same thing as the graph before, except with actual numbers. So in this work, basically what we just look at the bottom row, maybe we started with a circuit with 50 qubits and roughly 2.5 thousand gates, and we only added extra 18 qubits, and we had to reject one shot every 10,000 shots roughly. And this gave us a fidelity boost of this factor, like 235, which is quite a large fidelity gain. And what we can do is try to compare using what will be the overhead using QEC or PEC to achieve the same fidelity boost. And if you look at QEC, basically you can just run those numbers into surface code, for instance, and assess how many extra qubits you will need for a 50 qubit payload to run with this error rate, basically. And you will get a number that's close to 2,000 and roughly 2.5 thousand qubits. So here we just have like 68 qubits. And if we were to do the same thing using quantum error correction, you would go to this number of qubits. And you can do the same thing for PEC, for instance, so quantum error mitigation techniques. If you want samples with this fidelity, with PEC, with this noise, this layer fidelity, which corresponds to basically the noise we inject at each layer, you will need like billions of shots to achieve the same result. Except in our case, we are in the 10,000 shots, so like we have a 10 to the 5 improvement compared to PEC. So this seems like a very promising techniques to actually scale up error detection to interesting regimes, as long like while we wait, of course, for quantum error correction. So we did another experiment, which was trying to prepare a very large GAZ state onto our machines. And those states are very lowly entangled compared to the one we generated in the previous experiment, but they are very useful for many applications. So we figured might as well try to do the best possible GHZ and the largest possible GHZ using these techniques. So the idea of the experiment is you start from one qubit on which you apply a Hadamard gate, and then you kind of snake through the layout of the qubits by propagating CNOT gates to all the blue qubits. And then at the end, all those pink qubits correspond to check qubits that will just do a parity check between the two neighboring data qubits. And since we expect for a GHZ state to always measure the same parity, we can post-select away everything that gives odd parity between the two data qubits. So every time one of these pink qubit detects odd parity of qubits on the two neighboring qubits, we will reject the computation. And okay, I'm just going through this quickly, but the idea is that we can basically we know that this pink check here we can exactly characterize what will be the coverage of that check. Like what are the errors that will cut by this pink qubit. And this is done by basically going back towards the root of the circuit, which is this green vertex here, on either end of the check. So going this way, and look for the first common ancestor. And this will give us the region where errors are caught. So using this, we can actually look at the hardware and have a very simple algorithm that, first of all, discards any bad node or edge in the hardware that has a too high error rate, and crawl through the hardware and optimize the position of each pink qubit in order to maximize the amount of errors that are caught by those checks. And then we can iterate this process many times in order to find the best possible layout and then run the corresponding experiment. So what we did is to scale up to a very large number of qubits. So here we went up to more than 140 qubits. And we can compute different metrics. So one of them is Hellinger fidelity. So if we measure all qubits, we expect to only have 0, 0, 0 or 1, 1, 1, 1, since it's a GHZ state. So what you can do is like measure samples and compare the distance between, and compute the distance between the probability distribution we get and this peaked distribution of only zeros and only one. And this is called the Hellinger fidelity. And you can see here that basically I have four curves here. So the pure deep purple curve here corresponds to the raw circuit. Like you just run the circuit, measure the qubits, and compute the fidelity you get. And you can see that this quickly drops. And here we set some arbitrary threshold to 0.5, meaning that half of the time we prepared the correct state. And you can see that if you go beyond, let's say, 30 qubits, you fall under this threshold. If we add circuit error detection, which is basically our pink checks, we get slightly better results where we can basically drive the size up to, let's say, 50 qubits. We can also do something that we call device error detection. So basically, we can talk to the hardware team and they will tell us that in some cases, the hardware gets bad behavior, and we can post-select onto this bad behavior and reject runs where the QPU failed, basically. And this gives us a slightly better post-selection, basically bringing the size of the GHZ up to 60 qubits. And we can also mitigate for readout errors. So this is done using a statistical technique called M3. And this actually removes the last errors that we had. And we can go up, for instance, here to 120 qubits in this experiment. There are other fidelity estimate techniques. So for instance, we can measure random stabilizers of the state. And this gives us some comparable results in terms of assessment and Hellinger fidelity. So they kind of coincide, which is cool. At the bottom here, you have a rough idea of the post-selection rate. So if we run the raw circuit, we get no post-selection at all. If we run just the Pauli checks, we kind of discard a fraction of the runs. And the hardware, the device error detection, we reject almost the same fraction of runs it just adds another order of magnitude of discards compared to the Pauli checks discarding. We also ran an experiment of, instead of applying a Hadamard gate at the beginning, we apply a RY gate with some phase, meaning that we expect the fraction of zeros and ones to oscillate and form this type of curves here. And we actually observe this phenomena quite easily in the device. So this is a result where we had 100 qubits on a chip called IBM Kingston. But on top of that, we also ran some very recently on some new QPUs that actually we had access to only 2 weeks ago. We ran a 140 qubit experiment, and we managed to go above 0.5 fidelity, meaning that we produced a 140 GHZ state, qubit GHZ state onto this quantum chip, and we basically get the same, roughly the same type of fidelity assessment, where we are at 0.6 fidelity for this very large circuit. And this is how the experiment looks like in 3D. So here I plotted the layout at the bottom, and you can see all the blue boxes are the CNOT gates that are used to actually build the GHG state, and those orange boxes are the check gates that probe two neighboring qubits. You can see it on the layout here. So here space is basically the bottom plane, and time goes up. So what comes next? I think the most exciting thing we are trying to explore currently is the idea of combining this technique using PEC. So PEC is a quantum error mitigation technique, which has the cool property of giving you unbiased estimates of some expected value, meaning that you can actually trust the result of PEC to be exactly what you should have if no noise was present inside the circuit. So the main issue, as I mentioned at the beginning, is that PEC comes with a scaling that scales at 1 over the fidelity of your state to the 4, which is huge, and usually you can't scale too much the size of the experiment you can run. But the idea would be to, for instance, consider this green curve here. We could start with the original fidelity, which is roughly 0.4, and use error detection to bring this fidelity up to some way better fidelity, say 0.8 here, and then close the final gap using PEC. So we will do most of the work using error detection, and then close the gap using PEC, which gives us, let's say, guarantees that the gap is actually completely closed, and we have a good assessment of the result we expect. And we can easily compute the overhead of combining both techniques, basically by by multiplying the overhead of going from F to F prime using error detection, and then from F prime to 1 using PEC. And this gives us this type of scaling here, which roughly boils down to 1 over the post-selection rate of error detection times some quantity that qualifies the remaining noise, which we call gamma here, squared. And we can run simulations to see how it will deal with, for instance, a 100 by 100 qubit circuit using this hybrid technique. And we can run this experiment by adding more and more checks. So this is not an experiment, right? Sorry, it's a simulation. So if we add 0 checks and we have a gate error, let's say of 0.3, we end up with a gate with a sample overhead of 10 to the 11, which is untractable. Currently, we can do basically 10 to the 8 shots, but not 10 to the 11. This will take us 3 years of QPU time. But by adding more and more checks, we can bring this overhead down below this arbitrary threshold, which corresponds to 1 day of computation, roughly. So if we add, for instance, 30 checks, we can bring it down to 10 to the 5 shots, which takes minutes, basically. So it means that we can turn a 3 years experiment into a minute experiment just by adding error detection before running PEC. So this is quite promising, and this is what we are currently trying to do. So in conclusion, what we presented here is some ways to detect errors in Clifford-dominated circuits, and we have all the mathematical tools to actually find valid checks, score them, pick the best one, and implement it. And the approach we took can work for any qubit connectivity graph on any layout, even other devices and IBM's devices. It's not restricted to superconducting qubits. And we managed to actually scale experiments up to 2,500 gates, or 140 actually qubit GHZ state. And all of that by using only 18 extra qubits for the 50 logical qubits experiment. To give you a rough idea, if you were to use an actual quantum error detection code, like for instance a 422 code, you would require 100 physical qubits for those 50 logical qubits. And this is not even counting on the gate overhead that would be implied by implementing actual logical operations onto those encoded qubits. So there are still many open questions. For instance, here we only do very ad hoc code where we detect errors, but there are questions on, can we pick better checks such that we can actually correct errors, and there are some recent works that show that we can actually do that in some regime. And maybe also here we only worked on very random circuits or very highly structured circuits, but like GHG circuit, but maybe there is a middle ground where we can find still good approaches for interesting circuits. And the main question that I'm interested in is how can we use this technique to actually do post-selected quantum advantage experiments. So basically, can we apply this technique to interesting advantage experiments, such as, for instance, SKQD or other approaches? For instance, our group published a paper where we run a Krylov diagonalization process that relies on preparing a very large GHZ. And we haven't tried yet to actually use our better GHZ preparation and plugging that to their experiment. And maybe this would improve greatly the experiment itself. So there are many things to try using those techniques, and it's quite exciting. So thank you very much for your attention. And those are the two papers I mentioned in this work. So the left one is the one where we describe those space-time codes, and the right one is the one where we describe the large GHZ experiment. It's the most recent one. Thank you.
Thank you.
Thank you.
The session is now open for questions. If anyone has questions, you can please unmute yourself and ask the question. Or if we have questions on site, that's also most welcome. Or if anyone have a question, they can also write in the chat box. Okay, if not, then we thank everyone again for joining and for the wonderful talk. Thank you so much.
Welcome.
I will have US.
You're going to use that one?
Yes. Or if not, you can join the meeting by your.
Okay, we are preparing for the next talk. Can you share the screen?
Yeah, sure.
So we'll start the next session now. For the next session, we are happy to have Dr. Harshit Varma, and he will today talk to us on how to optimize energy consumption on BEQ. Harshit holds an integrated MTech in engineering physics from Indian Institute of Technology, BHU Varanasi, where he graduated in 2017. He went on to complete his PhD in physics at the University of Queensland, Australia in 2023. Currently, he is a quantum computing researcher based in Singapore and affiliated with Center for Quantum Technology at National University Singapore and CNRS here. His research spans quantum thermodynamics, causal orders in quantum process, and the energetics of quantum algorithm. He's going to talk today on how to optimize energy consumption of VQE. I welcome Dr. Harshit. Thank you.
Thank you for inviting me here, and I welcome everyone who is online to this session. And I saw the schedule, and there were a lot of talks about VQE, and today we have talks about quantum machine learning and stuff. So it has been an intensive week, I presume, and therefore I'll keep it as light as possible. So I'll include some technical results, but more or less I'll focus on giving an overview of why we should care about energy consumption of VQE, and is there a simple method as in we do not go to hardware specific details. Can we still discuss something about optimization of the energy consumption of VQEs? So most of the work that I will show here has been done with my team, which is present in Singapore and in France. So I'm affiliated with Majulab, which is a CNRS laboratory in Singapore. And it is headed by Dr. Alexia Offers, who is the director of Majulab. And this work has been done in collaboration with Rob, who is present in Grenoble, and Thomas, who is present in Evident, France, not very far from the location where we are currently sitting at. So the sponsors or the supporting agencies for this work are listed down there. So there's Majulab, there is CQT, which is Center for Quantum Technologies in Singapore, CNRS, the parent organization of Majulab, France BAC, which is a French project, ANR, SNQ, and Evident, for which we thank them for using their backend. So the first thing that I want to highlight is something simpler. So my goal here is to give you an overview of what we want to do. And therefore, what we want to investigate is how does law of diminishing returns work? So just to give an idea of what diminishing returns is, it means that for every input that you give, you gain certain output, and this performance of how much output will you extract from the given input kind of saturates over time. For instance, if you have devoted 10 hours to a study, does adding one more hour significantly enhance your understanding of the same thing, or you refresh your memory in the next day, and then you can still be on the high performance curve here, where every input counts more towards the output rather than being here. So these are the questions that we want to investigate as to how the law of diminishing return works. And this paradigm has been explored extensively in classical computing. So one of the problems that classical computing architectures or software engineers or other people are interested in is how many cores should I use? So my CPU, for instance, has 20 cores or 8 cores or 4 cores. And the question is, if I want to solve a certain problem in the most efficient manner, how many cores should I use? So each core performance does incur some significant energy cost. And therefore, I want to be in a regime where I'm optimally extracting the best value for every dollar that I spend or every euro that I spend in my energy. So let's say for a simple task such as reading a file, you could spread it over many CPUs, but what you will encounter is a plateau of performance, where the speed up that you gain for let's say using 2 CPUs versus 1 would be significantly less, say, than using 20 CPUs versus 8. And these costs or these diminishing returns arise because of various reasons. Some of those reasons are memory latency issues, or there could be some other trade-offs which are present due to the architecture of the computer or the problem itself. So how to formally explore these diminishing returns or trade-offs in a formal setting, especially for quantum computing? So we have a very beautiful framework which was introduced before. It's called metric noise resource, so in short MNR. which stands for metric noise resource. And what it says is, usually we know for a fact that more resources leads to better results. And the same question can be characterized by using a performance metric called efficiency, which says that efficiency is simply metric for how well have you done the task divided by the resources that you have invested in. So if we go to the previous slide, this means that the efficiency here in the curve where the slope is positive would be higher than the efficiency when you hit a plateau of diminishing return. So coming back to the problem in quantum computing, so the task here is more complicated than classical computing in some ways, and one of the ways in which this is true is noise. So the question then becomes, how do these metric and resources scale in the presence of noise? So technically you have a very noisy computation, and the question is, what is the best that you can extract from it, and what are the resources that you have to invest in order to extract those results? Exactly. So what we want to do is, how do we optimize over various control parameters? So these control parameters are knobs that you can control. It could be, for instance, the temperature that you keep the qubits at. It could be the size of the code or the size of the circuit that you want to run the calculation for, and so on. So these questions can be formalized into MNR kind of problem, where the question is, how does noise, which is a function of the CI control parameters, affect a certain calculation which happens in the quantum part? And how does the metric of performance or a certain measure of how well have you done the task look as a function of the control parameters CI? For doing this task, of course, you have to invest some resources, and those resources are also a function of these parameters called CI. In the simplest case, you can assume that this control parameter is, say, the temperature, and therefore you will encounter less noise if you run the quantum processor at a lower temperature, but you have to invest more towards the cooling cost in order to do that. So there exists this trade-off in terms of the control parameters that you need to optimize both the metric of performance or work under a constrained resource regime. So if you're given an energy budget, there is only a certain metric of performance that you can achieve, and that is, again, so you can work in the domain of either maximizing your metric of performance or working under resource constraint setting where you are given a limited budget of resources. So this was introduced in a previous paper by some of my colleagues, and it formalizes how to explore the trade-offs between noise, resource, and the energy cost in the case of quantum computation. So just to re-emphasize, the unique thing of or feature of doing quantum computation, which is essentially a bad thing, is noise, and therefore noise affects the metric, and the noise also determines how much resources would you need in order to do the computation. Now these three things are interconnected, and they can again be formalized in terms of efficiency. That is to say, what is the metric of performance that you get? Let's say, what is the accuracy of the results that you achieved versus how much resources you had to invest. So that is what efficiency determines. Now that picture was simple. We talked about having temperature as one of the knobs for controlling how well you do your computation. But there is a certain caveat to it. And the caveat is, as in the case of classical computing, quantum computing is also not a single box that you work with, but there are various layers or a stack representation of a quantum computation, where the actual computation happens on the level of QPU. So you typically have a noisy QPU, and then you have some enabling technologies such as cooling technology or readout or control electronics and so on. So this layered approach can be projected onto the MNR space, where we talk about efficiencies on the level of quantum computation, that is on the QPU layer, or we talk about efficiencies on the level of user, where there could be different metric of performance. So the flexibility of MNR allows us to use this stack model to determine the metric noise and resource and the efficiencies at any level of the stack. For instance, we can talk about the gate level. So each gate has a certain metric of performance, and that's called gate fidelity. And the parameters that could affect this metric and the resource consumption for each gate are your enabling technologies, say how well did you cool your system, how good the qubit is in the first place, say what is the decoherence rates and other things. And then the question is how good your control system or your readout system is. So implementing a gate carries these trade-offs. The more the resources that you invest, you might get better gate fidelity, but you might end up spending more in terms of the energy that you have to invest. A similar analysis is also true on the system or the circuit level, where now the metric of performance becomes the circuit fidelity or the success rate of carrying out, let's say, a computation for the given circuit. In order to affect the success rate or the circuit fidelity, you should ideally optimize over the metric of performance of the qubit, that is the gate fidelity itself, as well as you should implement clever routines for compilation, transpilation, or error management, and so on, in order to increase your success fidelity. Again, there are trade-offs. So the more energy you invest, or the better the compilation or transpilation that you do, or you implement some quantum error mitigation techniques. In that case, you can increase the circuit fidelity, but it comes at the cost of investing more energy. The same analysis is true when you talk about the user level, in which case we are talking on the top part of the stack, but which essentially is based on errors that propagate from the QPU to the upper layers of the stack, and therefore the final or the result, let's say, that you are interested in could be what is the error in the energy that I calculate for a molecule. So these tasks are typically EQE-oriented tasks, where you want to calculate the error in the ground state energy. In this case, what affects the metric and performance? So apart from everything that affects your circuit fidelity, your gate fidelity, and so on, it could also be the choice of post-processing, that is quantum error mitigation or other techniques. So you would have to invest more energy to get a better result. Now, one of the underlying things here is that noise that is a feature of quantum processors propagates from the lower level of the stack, that is the physical level, to onto the higher level of the stack, and therefore comes into picture at every level that we talk about. So each of these levels is dependent on the noise that happens on the lower level of the stack. One of the unifying features of this framework is we can talk about how much resources we invested, typically across the levels of the stack in terms of physical energy consumption. So I do not talk about, I may not talk about how many gates I have in terms of resources or other things, but rather I can say how much energy did my compilation cost, how much energy did my gates cost, how much energy did my error mitigation cost, and therefore I can define the efficiency metric across all the levels of the stack using this unifying measure. Now, zooming out of this case for quantum computation, why is energy consumption important? So one of the questions that people ask, or my colleagues in experimentation typically say, especially in universities, is we have free energy, in the sense they don't have to pay their electricity bills themselves, and therefore they are not bothered, especially on the prototypical level, where they have to make prototypes about what the energy consumption finally of a scaled version of a quantum computer will look like. But we have to keep this in perspective of what does, say, classical machine learning or other scalable AI technologies cost, and can we meet those demands in the future, or are we resource constrained? So the demand for AI-based compute or Gen AI compute, so that's a subset of AI that we are talking about, is projected to increase exponentially. And this is driven by, again, exponential increment in the compute resources that you would require in, say, the training phase of the algorithm, as well as in the inference phase. So for quantum computers, what it would look like is, if I know my gate cost today, can I project how much energy would I need for scalable or fault-tolerant quantum computers? Given that we have good gates which have like a certain energy, we have estimates for the post-processing, that is quantum error mitigation or PEC, as in the last talk, and so on. So could we have a model of energy consumption of a quantum computer, and how would it look like for large-scale computing? So again, bringing into perspective what we already have. So classical compute or AI compute used today is also has various components and is based on a stack, and therefore it is important to bring into perspective how much energy does it cost to do image generation or a simple question answer on a cloud-based large language model that you might use. So for a summarization task performed 1,000 times, you spend 7 watt-hours. For a text generation, it is close to 288 watt-hours and so on. So it gets quite close. So it gets quite steep quite fast. So based on the complexity of the task, we begin to see that the energy that you require to generate an image 1,000 times is close to what you would do by running a laptop for 20 hours. So this brings into consideration what kind of optimizations we need to perform in order to shift this, let's say, on the left side and so on. And it has been in fact the case that such optimizations have been pushed into AI over the last 50 years. So in the theoretical setting, the neural networks that we use came into existence about 50 years ago, but it took a lot of time to optimize, say, with respect to the model, constructing efficient algorithms, and then having the appropriate hardware, which is energy efficient, and engineering this all together into an architecture which is called a data center, and then optimizing energy efficiency of that data center. So this is a very complex problem spanning energy consumption of compute, memory, some other overheads, and other things which are environmental related. For instance, if my data center is based on solar power, I'll get cheaper energy in some months of the year as compared with other months of the year. And therefore, the optimization there would be more dependent on what time of the year is it, apart from setting everything all right in the algorithms or the hardware level. So these are complex questions that need to be understood, and people have been working on them. So my talk here is about what can we talk about for the scaling of energy consumption for variational quantum algorithms, particularly VQEs, as an example. So I saw that there have been talks and uploaded on YouTube about VQE. So I guess everybody is a bit familiar. A typical VQE looks like this. So you have a construction called an ansatz of quantum gates, and then you try to find what is the minimum energy of a molecule or a correlated system. And this is achieved by optimizing over a set of variational gates or variational parameters theta through a classical optimizer, and going through this loop and calling this classical optimization step every time in order to find the optimal set theta that minimizes the energy. The variational principle from quantum mechanics allows us to do these kind of tasks. And this is a simple representation of how this happens over many layers of the quantum circuit and many iterations of the classical optimization loop. So we will abstract from that setting. So we will, to gain clarity on what we want to achieve, we will see a very simple version of the circuit. So this consists of 3 parts. First, you initialize your state, you parameterize, you prepare a parameterized state through a quantum circuit, and then you do some kind of observable sampling. That is, you measure the energy of the molecule that you want to find, and then you try to optimize this parameter set theta through this classical optimizer. So there are two things that jump at us in terms of resources. So what are the resources that we see on the picture? One is how deep your circuit is. So how many gates have you used here in U theta? And how many times are you calling the optimizer? That is a number of iterations and iterations. The metric of performance that one could say for such an algorithm is accuracy, which is like how accurate your calculation is. The metric is defined as 1 minus accuracy because we want it to be monotonic. So a higher metric should reflect that we have done a better job than say a lower metric. So as accuracy goes up, the metric goes down. The metric saturates to 1, and that represents the best case that we have. So let's set up the problem. So let's take this simple representation and try to find a toy model to work with. So based on MNR, which is metric, noise, and resource, we have defined our metric to be 1 minus accuracy. We have the resources that you want to consider, and we have the noise that happens on the circuit level, and we model with something called a global depolarizing noise. So this is the formal setting. We have considered a model called the Heisenberg model, which is not important. The results will remain, will change, but they will remain qualitatively same for other models that you could consider. And then we designed a circuit based on a simple construction called the Hamiltonian variational ansatz. So this is a way to take the Hamiltonian and construct a circuit which will give you ground state of that Hamiltonian. This is based again on a number of variational gates. So the thetas that you see here are optimization parameters, and one layer is shown here for brevity. And then you could have multiple layers of this.
Sorry, I have a question.
Yes.
What's the physical problem that we are trying to solve with this Hamiltonian?
So as I said, this is the MNR framework. We're talking about how much resources should I invest for a noisy quantum processor to do the task most efficiently.
No, but I'm talking about the Hamiltonian. Like what's Hamiltonian? What's the representation of it?
So, okay, so this Hamiltonian has been found to be useful in describing certain materials.
Okay.
But you could use other Hamiltonians as well. So this is called the Heisenberg model of the Hamiltonian. You have a spin chain. Physically, how it looks like is you have a spin chain, and the nearest the points on the chain are interacting.
The neighbors of
Exactly.
Okay.
So this is a nearest neighbor type interaction. Yes.
So that is an lambda example. So you just want to see in the end how many energy that you have to consume for a typical problem, right?
Yes. So the most naive thing you can do is you can just plug in and you can check what the energy consumption is, but it will not give you insight over what to optimize. So is it that you're spending more energy on number of iterations or number of gates? Is there a particular point where this is the best, like the number of gates versus number of iterations and so on? And the second question is, how does noise affect it? So can you make projections of when the noisy processors will be better, how much energy you will have to spend? Or can you design a methodology in which you can predict how many iterations and how many gates would you need?
This will depend on the complexity of the problem.
Yes, so what I've shown here is a toy model, and it is a way to approach it. There are other ways. So the other way could be that you don't fix the circuit. There are adaptive ways. So you construct the circuit as you go. You insert one operator, one variational gate, and then you see how the loss is affected, and then you insert another one and so on. So these are different approaches of doing the same thing. But what I'm going to show here is one approach which gives you kind of the optimal gates and the optimal iterations in the presence of noise. So this is a toy model where I define a toy model to work with for the problem statement that we have. So one of the things that we were interested in is doing this energy optimization in a hardware agnostic way. That is to say that we do not want to stick to a particular hardware. If you take the circuit on the previous slide, this would look different for different hardwares. So if you were to run it on IBM, I would have to transpile these gates onto something that IBM can do on the gate level. If I were to run it on, say, some other platform, I would have to transpile these gates in order to do that. But one of the things that we found is, can we do it in hardware agnostic way? That is, by considering a very minimal transpilation, I deconstruct these gates into some minimal transpilation, and can I extract some meaningful results? So the transpilation that we use here is a very simple one. So we break down ZZ gates, YY gates, and XX gates using the blocks that are shown in red, green, and slight blue here for the same layers. So the layers that were shown in the first slide are the same layers shown here, but now we have gates which have been transpiled. The second assumption that we make is that the relative durations of the gates are same. And then we use these to insert the identities at our appropriate points. Why identities? Why could not we just run this and see how well we are doing? The thing there is that in most of the platforms, so even if I'm not saying a particular platform, but in most platforms, you have to keep your qubit. You have to do something to your qubit to make it stable or decoherence free, even when it is not operating. So if you are running, say, qubit 2, or you're running qubit 2 in this C0 gate here, what happens at the qubit 5? So you have to do something, you have to spend some energy in order to keep it decoherence free. And therefore, we assume that identity gates or idle times are also resources in some way. Now, one thing is clear here is from the VQE talks that you would have attended, you would see that more layers typically leads to better result. So I keep on stacking these layers ahead of each other in a sequential manner, and that enhances the so-called expressivity of my anthads. And then I can get closer to the actual ground state than I would typically do with, say, one layer or two layers. But what is the role of noise here then? So when each gate is noisy, then you would encounter some trade-offs. So the more deeper you go, you also accumulate noise. And then the question is, you begin to lose out on the accuracy after some number of layers. So these are the kind of trade-offs that you can investigate without going into the deeper details of how the circuit is made or how the computations are actually performed. So in some way, if you remember the stack layered approach, on the level of the stack, we are sitting on the algorithmic layer. So we are talking about number of iterations and number of gates, assuming that the processes are noisy, but not talking about how each gate is implemented separately or how does the actual hardware setup look like. So we transform that intuition into a schematic. What we learned from the last figure is we keep on stacking gates, but if those gates are noisy, that would lead to some trade-offs in accuracy. So let's say I have the ground state energy here on the y-axis, and on the x-axis I have the number of layers or the number of gates that I use to construct the circuit. So in the case of no noise, I would be converging very quickly towards the no noise exact value, which is the ground state of the molecule I want to describe or the system that I want to describe it for without any noise. So that's shown in purple here. But as I begin to increase my noise level, that is, if each gate is noisy, depending on the noise, I will begin to lose off on the accuracy as I add more layers. So there exists, from our intuition, we see that there exists some optimal point, simply in terms of number of layers, where my calculation is it is best performance and least resource intensive that I can do. So those points would be somewhere here. That is indeed what we observe from running a simple VQ algorithm. So the participants who have attended this workshop are invited to try it in any SDK that they work with, maybe Qiskit. We have worked with a different SDK which allows us to define the noise per gate and so on. And what we see here is if I were to give it enough iterations, that is, I allow the algorithm to converge, the true ground state for a simple toy model is somewhere here. And in absence of noise, as I increase the number of gates, which is shown on the x-axis, I converge towards the true result. But as noise is increased, so I go from blue to orange to green and so on, I begin to see these trade-offs, and which is prominently visible here in the pink color, where I cannot go in fact, to the results that I actually want. Yes.
What is epsilon in this case?
It is you can talk in terms of the average noise level per gate.
You use a model of noise.
Yes. So we have used global depolarizing noise model. I'll just introduce it. So this is just for illustrating that the intuition that we developed here. Under any noise model that you use, if it is associated with the gates, number of gates, you would see these trade-offs. Maybe the nature of the trade-offs will be different. Maybe the points will be different, but you will see these trade-offs under any kind of noise which accumulates with the circuit depth.
What type of noise did you take into account in your?
So I'll come to that. This was just for illustrating that the intuition that we developed was correct. Now we come back and we see that we missed out on one detail, and that was about, exactly as asked, what is the kind of noise that we consider, and also how does the number of iterations, how do we introduce number of iterations in this game? So again, we'll talk a bit abstract in the sense we do not want to make a hardware phase model of how the energy consumption works, but hardware agnostic model. So we move towards scaling laws. So in classical compute, there are some things called scaling laws, and these laws are about how many parameters do I need to solve a particular problem, or what is the number of tokens that I require in order to solve that problem, or how much compute do I need to solve that problem, and how does it scale with the problem size, or how does the accuracy of what I want to achieve scale with compute or training time or anything, or the memory. So these are well-known scaling laws in other parts of classical computation and AI, and therefore we will one of which is illustrated here. I'm giving you the inspiration of what we want to do. So we want to have scaling laws which say, how would my accuracy look like if I increase the circuit size in presence of noise, or I increase my number of iterations and so on. So an example is given here for the classical computing case where the loss which you want to maximize scales with compute with certain power law, scales with the data size and the number of parameters for a particular problem that you want to do. In this case, it was about predicting the next word. So why are scaling laws important? So let's say if your law scales as x to the power minus alpha, where alpha is very small, then you can extract those coefficients, and you can see that if you have 2x the times of resources, you gain, say, 3% accuracy or any other metric with respect to doubling the compute, or 6% by doubling the data set, or 5% by doubling the parameters. But you begin to lose out on the gains. That is, the gains that you have as you 10x the resources are much less in the sense of per energy input that you have given per compute or per data set as compared with the 2xing the resources. Similarly, you see by 100xing the resources, you can do even better, but you are begin to touch the plateau of diminishing returns in some way. So let's come back to the case that we have. So we had this toy model, and then we construct scaling laws for VQE. And one of the first scaling law we have is how does your VQE converge with respect to number of gates? So we allowed it to have as many iterations as it wanted. And we saw that one of the scaling laws that we found is that it exponentially converges to the ground state in the case of noiseless computation as you increase the number of gates. And on the y-axis, what I've shown here is the error, which goes to 0 as the number of gate approaches, say around 600 or 700 for the problem that we have. And this convergence is in fact exponential, illustrated by points around 150 and 300. So you have these points, and we see it exponentially converges. So this is the first scaling law that we found. The second is how does it converge with respect to number of iterations? So for each depth of the circuit, that is number of layers, we plot how many iterations did it take to reach a certain convergence limit, and therefore we could formulate the scaling law based on a factor called mu, which is dependent on the number of gates. So the more gates you have, the longer you will take to converge, because you're optimizing over all the gates, and therefore this factor mu, which is the convergence rate with respect to number of iterations, is also a function of number of gates. So this is the second scaling law that we formulate. The third is, of course, the noise model, which I did not introduce before. So we assume a global depolarizing noise model in the circuit, which is a commonly used noise model in order to study noise. So what it means is, for a given noise, say epsilon, I would solve the problem accurately by a factor of 1 minus epsilon to a power of calligraphic n. And then I could also fail with a probability of 1 minus epsilon to the power calligraphic n. Now, this is for, say, this is for a calligraphic n, but we can assume that calligraphic n is equal to the number of gates or a certain factor of number of gates if we were to relate like the noise with the gate. So we replace this n by ng in our calculations. We also find how does the convergence rate mu or nu look with respect to number of gates. So this is again a phenomenological trend or a scaling relation that we find. And thus what we do next is we combine all of these. So some of these were in the absence of noise with something that we know about the noise or the nature of the noise, and construct a general relation for for the energy that you calculate through VQE as a function of number of iterations and number of gates minus the ground state, which is basically the accuracy. So having access to this pipeline where I can build scaling laws and I can build the energy consumption models, you can explore what are the trade-offs on this hardware agnostic resource consumption play. So what I show here is the total number of gate operations, that is number of iterations times number of gates. So that's the background for this optimization. The green dotted lines here are the error curves. So if my error is 0.01, I am on this line. If it is 0.02, I'm on another line, and so on. The magenta curves just illustrate the contours of the delta heat map here. So moving from 10 to the power 6 to 10 to the power 5, that is an order of magnitude more gate operations. So we can ask the kind of questions like, if I were to keep the metric as 0.01, what is the minimum number of gates and times the number of iterations that I would need? Or I could ask another question is, given I have 10 to the power 6 gate operations, what is the best in errors that I can do? So these kind of optimizations are possible. What I show here on the as a blue star is in fact moving on the isometric curve. So fixing my error and finding the optimal point of least resource consumption or least resource cost in terms of delta. So we can also formalize the question, as I said, in terms of moving on the resource constraint. So if I said that I have a certain budget of doing the operations, I can move along those budget lines and find what is the best error that I encounter. And that's what is shown here. So what is shown here is the efficiency, that is the metric time divided by the total resource as a function of the total resource cost, moving along one of these lines. The magenta lines that you see here, what is the best metric that I get as a function of on what line am I moving? So that's what is shown here. What I see also is the efficiency with respect to the total number of resources. And what we see is an efficiency frontier, that if you begin to invest more resource, you gain on the efficiency until you hit a certain point after which your efficiency begins to fall. And typical of the diminishing returns, we also see that the metric saturates with respect to the total number of gate operations as we increase the number of gate operations. So this defines an efficiency frontier for VQE based on scaling model, which is one of our main results. Now we can also look on for the same result on the efficiency landscape. So now the heat map is efficiency, more green is better efficiency, and therefore again the stars remaining the same because the optimizations that we perform are for each given isometric curve, what is the least number of resources that I need, and that would also typically maximize the efficiency. So let's say for the example of 0.02, it's just in the more green region here than somewhere here, and that's because the efficiency is maximized on the star for the star. So let's come back to the model that we had. So the objective here was, could we define the metric in terms of resources that we invest and in terms of reasonable model of noise that we have, and that it did indeed show for the two kind of resources that we consider, and that's number of iterations and number of gates. Now the question here is, can I characterize better the classical energy consumption that I had for the classical resource cost that I have? And indeed I can. So there is a metric, or there is a performance metric used in classical computing, and the resource count for which is FLOP, that is floating point operations. So the question that I ask here is, how many flops are required for performing the optimization? So that result we could get from doing the full VQE emulation. So we do it on a computer, we find how many flops were required for doing the entire VQE, and then subtracting it from the emulation required only for executing the circuit. So in a VQE, there are two major things. One is iteration, the other is circuit. When you remove the cost of emulating the circuit, you're left with emulation of iterations, and that we could benchmark. So using some of the known routines for such benchmarking, we found how many floating point operations are required. So for a complete VQE run, we found that the flop scales exponentially with the number of layers, but only QPU emulation requires a linear number of flops for emulation, and therefore by subtracting one from the other, we could find how many flops are required for doing the optimization alone. So why are we interested in this? Is that we had an abstract plane where we performed the optimization. So we had this plane where we found the minimal energy consumption for a given metric was these stars. And therefore, we want to know, how does this landscape change? How do these lines change if I associate a cost with the number of iterations and a cost with the number of gates? So this delta n iterations times ng gives the same weightage to number of iterations and number of gates. So the question was, being hardware agnostic, can we assign certain weightage to each of these operations? So what we do, assume a certain resource cost of the gate based on a particular architecture. So now we are marrying hardware-based stuff with hardware-agnostic stuff. We add our understanding of the flop required for performing the optimization that we benchmark with the green 500 efficiency for doing a certain number of flop. On the so we marry the quantum hardware energy consumption with classical hardware energy consumption with the optimization landscape that we had before, and then we see what we see is the landscape is distorted. So based on a certain assumed quantum hardware energy consumption and assumed informed iteration energy consumption, we see that the points shift now towards n iterations when you implement the same landscape on a physical energy map. So we characterized this shift from the hardware agnostic setting to that is the algorithmic landscape to the physical landscape by using the shifted values of the NG star and the NH star, that is the optimal number of gates and optimal number of iterations. And we found that there is a shift, there's a slight shift in the optimal gates and the optimal iterations that are required based on the understanding of the hardware that you have. So what this methodology allows us is first do a hardware agnostic optimization based on the scaling laws. Then you add your understanding of the hardware that you have in terms of the classical and the quantum part, and then you can effectively optimize over these settings without doing the whole process for the entire stack at each point of the calculation. So that is what I've shown here. So how do the optimal number of gates and optimal number of iterations scale when you move from the algorithmic landscape to the physical landscape? Here is a summary of what I've discussed till now. So the question here was to find algorithmic parameters for resource efficient computation. In order to answer that question, we developed a detailed methodology for energy efficient VQE. And we are in the process of validating our scaling laws or our understanding based on a real quantum device. Now we can use these tools that we build for energetic pipeline to find to make other derivatives such as benchmark based on energy consumption and resource optimization routines. This also motivates the standard for energy efficiency of quantum computers. That is to say which quantum computers are better than let's say we are comparing two quantum computers. How do we say based on energy efficiency that one is better than the other? So these kind of comparisons I will motivate. So one of the explorations that prototyping that we are doing is in terms of how much energy do I need to solve the VQE problem for a projected problem size. So I'm not going into the details. What we want to do is we want to marry the concepts of performance benchmarking with energetic benchmarking and find exactly how much value you have to spend in order to go to a certain accuracy, say, for a larger problem size. So this allows us to compare two quantum computers. So shown here is, let's say QC1 is a type of quantum computer, QC2 is another type. If I were just to look at one point of this, I would say that QC1 is more efficient than QC2. Sorry, QC2 is more efficient than QC1. But if I look at the scaling of how this efficiency goes with some metrics such as problem size, I could effectively say that indeed QC1 is doing better for larger problem sizes. So these are the scaling, these are the behaviors that we want to illustrate. And for that, what I used is comparing two types of circuit design, that is using two different answers than two different quantum computers for now. But this gives us insight about how to build these relations. We also did a breakdown of how much of this energy consumption is classical versus how much of it is quantum using the tools that we developed before, just to give an order of magnitude of how much percent-wise is it classical versus quantum. And therefore, so the benchmarking, why is it important, is because the design decisions for quantum computers, let's say if it is a hybrid algorithm, should be informed by the choices based on energetics rather than the performance metric alone. And therefore, these kind of breakdowns enable us to make roadmaps which are aware of the energy efficiency of the different parts of the computation that are happening. So there are more parts of the computation. As I said, we are looking at very top level approach, but there are other parts of the quantum processing protocol, and that includes various levels of the stack spread across three kinds of physics, that is information science, quantum physics, and classical physics. So it is a very complex question to tackle as to how to associate energy cost with each of these sections, and then give a roadmap of what we want to optimize for better solving a given problem. So what we do is we tackle these kind of questions in a working group under the IEEE framework. So we have IEEE P3329, which looks at how to define energy efficiency of quantum computers. And we we are working on a draft to formulate exactly how to break down the energy cost. How should companies or other actors report the energy cost, and how can we drive energy aware roadmaps based on these breakdowns. So that is it for now. Please feel free to discuss with me as I'm here for the day. Thank you.
Thank
Thank you
you.
for very nice presentation. I have one question about, because for estimate the consumption of energy is depend, you can, it will depend on a classical optimizer as well. I mean the method you use, I think it plays a big role as well.
So
Yes, so the yes, how many layers and so on.
yeah, so there are two parts of the problem. The first part is the quantum part. So that we discussed through scaling relations before. So this gives us access to these kind of plots where I can find through noiseless simulations and assuming a certain noise model, I can construct this whole space and say what is the optimal number of gates and number of layers required, sorry, number of gates and number of iterations required to do my task to within 0.01 error. So this is the first part where you do not assume any hardware. You assume that your circuit minimally represents any kind of hardware or any kind of setting, and then you implement this. The second part is, what if we have to assign values, like we have to say how costly the gates are actually when you implement them and how costly the iterations are. So that again, so that I showed in the second part, where first we benchmark how many flops are required for classical optimization. So per each iteration, how many classical compute resources do I require, given in terms of number of flops? So I measure the flop for VQE. So I do it, let's say 10 times, and I allow it to converge and so on. So per iteration, I know the number of iterations, so I can get the flop per seed per iteration. From that, I subtract only the cost of doing QPU emulation. Right now, we are doing everything on emulation. So what I want to know is how much classical optimizer cost, and that we have shown through by subtracting the flops required for VQE from the flop for the circuit emulation only. So we obtain some phenomenological results there also. So only for QPU emulation, it grows linearly up to certain circuit depth. For complete VQE, that is including classical optimization, it is exponential.
So did you try on any real hardware?
We are in the process of validating on real hardware. So A, the scaling relations, B, the classical computation.
What have you hardware?
So this gives a framework. What we want to do is, on the hardware level, let's say we can perform certain energetic efficiency optimization. So we want to look at hardware. Right now, we are working with Eviden on using IQM superconducting computer. So there are optimizations to be done, which can be done on circuit level also, chip level also, like the hardware chip. But we cannot have access to them right now. What I theoretically show here is that you can merge the concept of chip level optimization. That is, how much temperature should my chip be at, or how lengthy should my gates be, with the energy cost of classical optimization and the hardware agnostic optimization of resource cost that we did. So we can marry all three and we can get access to these kind of landscapes, which allow us to optimize based on the hardware rather than hardware agnostically. The advantage here is we do not have to do these calculations every time we run the computation. Rather, we can do these things independently using scaling laws, and then we project onto the physical landscape. Yes, so that's what I've shown here.
So will you apply for other type of hardwares in the future?
Yes, so that's a long-term goal. What we want to do is kind of energetic benchmarking of quantum computers. So using these kind of pipelines that we build, we can compare to quantum computers using benchmarking. So that's what we want to do in the longer term.
Very nice talk.
Okay. Let me see if there are any questions. Do we have any questions online? If yes, please unmute yourself and ask the question. If not, then we close this session and we will meet after the coffee break at 11:15 Central European Time. Please join us again.
We stay on online because we will have very nice talk later too. And we will have the hackathon opening section.
Yeah.